Hi, this episode of Shawley Physics is going to cover series and parallel resistors. This is my slightly more advanced AP version. I'm going to take you through how to find the equivalent resistance, and we'll learn about what that is in a second. But what is the equivalent resistance for these series and parallel resistors by looking at the potential differences and thinking about the current flow through each. So we're going to derive those formulas rather than just presenting them. So series resistors, of course, would indicate that those two resistors are in a line along the same branch, like in a series circuit. So I'm going to just make a simple circuit here with an EMF source, battery, call it 10 volts, 2 ohms, and 2 ohms. Okay, so you might have a guess here, but what do you think the sum or the equivalent resistance of these two resistors are going to be? Now, what does that term equivalent resistance mean? If we're going to turn this circuit into one with a single resistor, it's very much like finding equivalent capacitance, like we might have done before. Can we turn those two resistors into one resistor, and what would that value be? That is the equivalent resistance. Okay. So you might have a guess. If you're thinking 4 ohms, you're exactly right. But I just want to show you how to work that through and prove it. We're going to look at potentials. All right, we can look at several points on this circuit. As we go around the circuit, there's a potential difference of 10 ohms from here to here. I should put in my poles there. So there's a positive 10 volt potential difference between those two sides. Now notice this point and this point. Assuming there's very little resistance or negligible resistance in the wires, these 2 points have exactly the same potential. So we might, if I'm going to call this point C, B, and A, then both of these on this side, on the left side, would be point A. They're connected by a wire with a very insignificant amount of resistance. So if there's no resistance, then there's going to be no difference in potential energy. It would take no work at all to move an electron from this point to that point. That's what it means. And same thing over here. This would be point C as well. So points A and C are connecting the batteries, and they're also touching the outermost edges of this series set of resistors. So if we equate that to over here, we've got our A's and C points. Now B would be hidden in that equivalent resistance. If we were to look at these two resistors, take them apart here, there's a potential difference from A to B across, we'll call this resistor 1. And according to Ohm's law, or if you recall back from resistance, R equals V divided by I. Or simply look at my awesome shirt. Resistance is not futile. It is voltage divided by current. You remember that resistance is a ratio of potential difference across the resistor to the current flowing through it. So that's that ratio. Or you use V equals IR. So VAB would be V times the current. And the current through the battery is the same as the current through resistor 1 is the same as the current through resistor 2. All the electrons that pass out of the battery and through resistor 1 and through resistor 2, all of those pass through every single one of those elements. They can't go anywhere else. So they all have the same current through this entire path. I is going up that way, I is coming down this way. You can't escape that I. There's one single current. So I is the same for all resistors. But resistance is not, or may not be. Okay? So this would be VAB equals IR1. And how about B to C? That potential difference depends on the resistance value of resistor 2. So VBC equals IR2. All right? Now we've got to relate these together. The battery touches both sides here. Okay, or we really don't need to worry about the battery just yet. The battery is what's going to supply the current, it's going to supply the flow, but the resistance is still resistance. Those wires still have their properties to them. They don't require current to be flowing to be resistant to flow. So it's just the property. So VAC now is the potential difference across both of the resistors. Well, that sum is, you got to think about it like a hill. All right, if we're going to go from point A to point C, we're going to go down the hill. And these resistors are decreasing energy. It's like decreasing gravitational potential energy, except they're decreasing electric potential energy here. That's why we have a change in potential. So VAC is the same as the sum of VAB and VBC. All right, and that's what relates these two together. So from this point to this point, we've got a VAC. Now, what is VAC? VAC is also the potential difference across our equivalent resistance that we're looking for. So we're going to use a I times equivalent resistance to substitute for VAC. We're going to substitute I R1 for VAB, and we're going to substitute I R2 for VBC. All right, and what happens here? Divide one term by I, divide the other side by I for the equivalence, keep them equivalent, then the I's cancel, and we've got this beautiful thing showing up here. The equivalent resistance for series resistors is just the sum of all those resistance values. So I just didn't pull that out of my hat. We're going to potential. This is where you can find it. All right, so that's series resistors. Just another quick example. If you've got 4 ohms, 3 ohms, and let's say 10 ohms without a battery, that equivalent resistance would just be the sum. 10 plus 3 plus 4, 17 ohms. All right. Now there's one more piece that we can figure out here, is the current. What is the current? We used it right in here. Okay, we're not going to just let it go, because each of these resistors are going to work against the EMF, the electromotive force from the battery or the cell, whatever's pushing it. So here in this case I've got 10 volts applied to 4 ohms of resistance from our first example. So what do we do to find the current? Well, go back to V equals IR. That has the current. So resistance is the ratio of V to I. We've got 10 volts. I's are unknown, and 4 ohms is the resistance. So there we see that the 10 is equal to 2.5 times 4, or 2.5 ohms. Right, so we got the I equaling 2.5. They say ohms, I meant amperes. 2.5 amperes. There it is. So there is a nutshell. There's a series. Now let's move on to parallel resistors now. All right. Now I could use 2 ohms again, but the result is very boring. So this time I'm going to use a 2 ohm resistor. And let's use something larger than 2 ohms. We'll go with 4 ohms now. We'll still hook this up to 10 volt battery now. There we go. If they exist. I think 10 volt batteries should be in existence. That sounds like a really good round number there. Okay, 10. Anyhow, parallel resistors. So we're just going to add them. 2 plus 4 equals 6. Well, keep in mind here, the current, there's a nice constant in the other one. It is not going to be the same for all branches of the circuit here. Because what happens to that current? Well, some electrons flow up one way and the other electrons flow down the other way. Not all electrons will go through all of the resistors in the same loop as they drift through the circuit. Let me bring up an example here. So instead of a series circuit, there's one pathway for electrons to flow. Okay. we're going to have a parallel circuit. Now in this case, the example I'm showing you here, we've got the same battery and the same two resistors, 10 ohms and 10 ohms. But we definitely see a greater flow in this section down here. You can see the ammeter, the current meter, it's measuring a much higher current. So here we can imagine this as instead of a single lane highway where all the cars need to travel in this one single path, the segment of this highway where there's resistance, where there's resistors in the circuit, it branches off into two different lanes. So instead of all that traffic moving through one lane where there's two areas of resistance, this traffic, in this case in the parallel circuit, can either go one pathway with only one resistor or the other. But remember, on these pathways you're only getting half the traffic, so half the cars. So we either have all the cars hitting two accidents or half the cars hitting one accident. Which one do you think is going to flow better? The 2 ohm resistance, 2 parallel resistor combination. That's one that's going to flow better. All right, so back to it. How do we figure out what to do? Well, 2 plus 4 is 6, right? Well, is it going to be less resistance? Should we subtract them? 2 minus 4 or 4 minus 2? It doesn't really make sense either. So let's go back to thinking about potentials and potential difference. Here you'll notice that there's two different ways that these electrons can go from the top of the hill to the bottom, or I should really say the positive charge. I made a little mistake here, didn't I? I labeled this the opposite way. So I had my flow going this way. So I could either change this to a positive and make that a negative, or I'll just reverse the flow here. Current flows from the positive side to the negative. The electrons flow from the negative to the positive. That's for a different lesson to talk about those holes moving, those positive holes. The current is flowing this way. So current will go from the highest potential toward the lowest potential. So the high side of the battery to the low side. So I will change this from A to B. Okay. I have no problem with screw-ups in this video because that brings up some very important points that I usually miss talking about. So again, this side of the battery is A, connects up to here. This side of the battery is B also. Now in this slope here, our ski slope, we can either go from the top of the hill down this left route through the 2 ohms of resistance, or from the top of the hill down this other route through the 4 ohms. Call it the bunny slope, where the flow might be slower, and the triple black diamond, where it's a lot faster. Whereas skiers are really moving there. They have two different ways. One has more resistance, one has less. It's also we're still going from the same altitude down to the same base of the mountain. So bringing it back, there's two different ways. And the right side of each resistor is connected to A, the left side of each resistor is connected to B. The potential difference across both resistors is the same. It's the same potential difference. In the series case, the thing that we had this being the same here was the current. The current was the same through each one, and they had potentially different gravitational, electric potentials. Here we have the same potential, but what will happen to that current? Some of the current's going to go this way, some of it's going to go this way. So there is if we call this resistor 1 and resistor 2, we will have an I1 up top and an I2 down below. And now those current values, the charges, there I go again. My arrows are all backwards here. Maybe I should have just gone from switching the positives and negatives. Well, let's reverse this. We'll make that a dot, and we'll make that our arrows. Dots and arrows. Dots and arrows. It's magic. So here we have the current splitting up. Excellent. Dots and arrows. Gotta love Shelley screw-ups. You should have a new channel called Shelley Screw-ups. I'll post them all there. Okay. So now we have the current going in the correct direction of flow. I going across 2 ohms, I2 going across 4 ohms of resistance. Okay, so let's go back to the potentials, like I said. VAB is the potential difference across R1. So we're going to have an I1, R1. That's for that top branch there, right? But we also have VAB being the potential difference across this resistor too. So we're going to have an I2, R2. All right, where are we going to go with this? But remember, what we're trying to do is convert this circuit into one where we can envision those two resistors combining into one equivalent resistance value. So if this is still B and this is still A, then we also have VAB equal to, what will this be? Well, that's I coming out of there. That the total resistance, or that battery, sorry, I shouldn't say total resistance, the battery current, the current going through the battery here, it's going to be the flow through this equivalent resistance. So I've got another I times equivalent resistance. All right. So you might be looking at us going, do we make them all equal? Well, you could, but there's one more piece of information here. What happens? What is the relationship between I and I1 and I2? What happens to that I when it hits that junction? It splits up. So the sum of the current, sum of the I1 plus I2, is equal to the I going in. The current that flows out of the battery and into this junction is equal to the flow that goes out. All right, let's look at those electrons in the parallel circuit there. The electrons that are going in here, some go down this way, others go up this way, and they recombine and move through the battery. Okay? Now, so what's this all mean? That I is equal to the sum of the other two. This is something we're going to come back to. Oops, I did 2 and 1. Okay, backwards. 1 and 2, 2 and 1, doesn't matter. This is something we're going to come back to. It's called the Junction Rule, Kirchhoff's Junction Rule. We're going to get back to that later on. Don't worry about that for now. So we also have this relationship, I equals I2 plus I1. All right. So I have all these V equals IR values. If we solve each one for I, just in general, I would be V divided by R. So I for the equivalent resistance would be VAB divided by RE. So what I'm doing is I am substituting VAB over RE for I from this expression there. Now let's go to I2 and R2. Let's get that one. I2 is equivalent to VAB divided by R2. VAB over R2. There it is. Plus I1. That's going to be a VAB going up here. VAB divided by R1. Excellent. Very classy. All right. So now look at this expression. What do we got here? Well, if we factor out a VAB from all these terms and divide them on both sides, they would cancel. And what we're left with is not an R equals R2 plus R1, but a 1 over equivalent resistance equals, I'm going to reorder these again, 1 over R1 plus 1 over R2. There it is. And you know what? If we had a third branch or a fourth branch, we would keep adding them. So this is for parallel resistors. Okay, resistors in parallel. Now, an example of more than one, more than two resistors. I'll give that here just as a brief example. You might have 3 stacked together, or 4, or 5. Okay, there's any number of parallel branches that you could put together. But let's go ahead and solve this with the values in there. We've got 2 ohms and 4 ohms. I'm going to do it off to the side here. We've got 1 over the equivalent resistance 1 over RE equals 1 over 2 plus 1 over 4. All right. So for sum these, of course, that's not 1/6. We've got to find a common denominator. So 1/2 is the same as 2/4 plus 1/4. And then we'd have 2/4 plus 1/4 is 3/4. Now we want to find the equivalent resistance from that, solve for RE. I like flipping them. 1 over RE is to 3 over 4, as R over 1 is to 4 over 3. So it's 1 1/3 ohms. All right. So 2 plus 4 is 1.33, at least in parallel resistor sense. All right. So that's how you carry it out in practicality. If we now take that, let's follow the last step. Let's find the current. Given the 10 volts and the equivalent resistance of, let me go back to the fraction here, 4/3. All right, and we solve for I. I would be 30 over 4, or 10 times 3 over 4. And that's 15 over 2, or 7.5 amperes. All right, there we go. So the next thing we're going to do is look into combination circuits and fitting a few more of these together, but that's the basis of where these equations for series and parallel resistors come from. Thank you for watching.